In this video I'm going to look at 4 examples dealing with spheres. The first one, I have a sphere, as you can see, and it's cut by a plane, plane P, and that plane creates a circle inside of my sphere right here. So as you look at this, it tells you that O is the center of the sphere, and plane P is intersecting the sphere like I talked about in circle R. Now if the length of segment OR equals 6 centimeters, so this piece right here, which is right here, we know that's 6 centimeters long, and we know the length of segment OS, that would be this segment right here, is 14 centimeters long. We want to be able to calculate the length of segment RS, which would be right here. Now, something that you need to know about spheres is that if you create an angle that goes from the center of the sphere to a circle that's in the sphere to then a point that's on that circle, that will become a right angle. Well, then if I have a right angle with my green and my orange segments, I'm going to have a right triangle in my sphere. Well, then if I want to find the length of one of the sides of the right triangle, well, I'm going to use the Pythagorean theorem. So as I do that, I'm going to have a squared, which I don't know, so a squared plus my b is 6, square that, and it's going to be equal to my c, 14 squared. Now I just have to go through and I have to solve my equation. I'm going to have a squared plus 36 equal to 196. Now if I subtract 36 from both sides, I find out that a squared equals 160. And as I continue on, I'm going to take the square root of both sides. I'm going to find out that a equals, now remember, don't forget we're going to have the plus or minus. Now I'm going to go for the exact, so what I'm going to do is I'm going to look at factors of 160 to do this. I see it's even, so I know 2 is a factor. Well, 2 times what is 160? That would be 80. I can factor the 80 some more. That would be 2 and 40. 40 would be 2 and 20. 20 is 2 and 10, and 10 is 2 and 5. So those should be all my factors. Now if I go through and I multiply these all back together, it will come out to be 160. Now what I do is, when I simplify this, I look for pairs. I see a pair of 2s, I see another pair of 2s, which means I can take out a 2 for this pair, or I can take out 2 2s because there's 2 pairs of 2s. Therefore, when I take it out, I'm going to end up with 4 on the outside. So I'll leave the plus or minus there. So I'm going to have 4, then times the square root of that 2 and that 5 I can multiply back together. Now, being I'm looking for the length of a segment in my sphere, I can get rid of the negative, and my final answer would be the length of segment RS is equal to 4 root 10, and the labels on all of this was centimeters, so it would be centimeters. When you punch it on your calculator, you're going to get an approximate value of 12.65 centimeters for the length of segment RS. Now my next one, I want to calculate the area of the rubber softball. It's a rubber softball that I've had in my classroom that, that I use for demonstration purposes. And what we need to know is, go back to your surface area formula. You know that the surface area of a sphere is equal to 4 times pi times r squared. So really all we need to know is the radius. Now the problem is calculating the radius, or measuring I should say the radius of the rubber softball is kind of difficult because we can't cut it in half, figure out where the center is, and then measure to the sphere of the softball. So what we're going to need to do is we'd have to measure we could measure the circumference with a tape measure, which I've done already. And you find out that the circumference of this rubber softball is 30.1 centimeters. Now that I can use because I can take and plug the 30.1 in for the circumference, and I know my circumference formula, circumference equals 2 times pi times r. And now it would be a matter of solving that equation. So if I take and divide both sides of my equation by 2 pi, I find out that the radius of my rubber softball is 4.79. And now that I have my radius, I can just come back over to my surface area formula and I can plug it in. The surface area is going to equal 4 times pi times the radius that I just found, 4.79, and then square that. After punching all of that on my calculator, I find out that the surface area of my rubber softball is 288.39 centimeters squared. Now what that tells me is, if you were to take 1 inch by 1 inch centimeters, little squares, 1 inch by 1 inch square centimeters, you'd be able to put 288.39 of those little squares would cover the outside of that rubber softball. Now here, my next one, I want to calculate the surface area of a sphere. Now this time it tells me that the area of the great circle is 38 square inches. Now remember, a great circle is a circle on the sphere that has the same center as the sphere. Well, if it has the same center, that means the radiuses of these two, of the sphere and the circle, are going to be equal in length. Well, if I go back to my surface area formula, 4 times pi times r squared, all we need is the radius. So one method here is to take and look at, well, we know the area of a circle is pi r squared, and in this problem, we know that area. We can plug it in. So we'd have 38 times pi times r squared, and now we can go through and we can solve this equation, figure out what r is, so we can plug it back into the surface area formula. This will get us down to r squared equaling 12.10, and I use the pi button on my calculator to do that. And then when I take the square root of both sides, I'm going to have r equal to, and then don't forget your plus or minus because you're solving, or you're using the square root in an equation. And we get 3.48. Remember, since we're dealing with the radius, the negative's not going to come into play, so we can don't have to worry about that. Now, come over here, plug that back in, so my surface area is going to equal 4 times pi times 3.48, and then squared. Now, when I type this on my calculator, I'm going to use that same 3.4, it's actually 3.47789, and it keeps going on. I'm going to use all those digits on my calculator, I'm going to square that, and then I'm going to multiply it by 4, and I'm going to multiply it by pi, and I end up with an answer of 152 for the surface area of this sphere. Do 152 square inches. That is one method to calculate the surface area of the sphere. Now another method looks like this. I'm going to take this formula here, area equals pi r squared. I'm going to take my other formula of the surface area is equal to 4 pi r squared. I'm going to look at some things here. Now we knew that the area of the circle was like this. So 38 equals pi r squared. Well, then I come over here to my surface area formula and I go, well, there's pi r squared right there. According to this equation, I could just replace the pi r squared over here with 38. So I could take 4, I can multiply it by 38. If I take 4 and I multiply it by 38, I end up with 152 square inches. Now, I don't care which approach you take, whether you take that first approach that I did up here, where I went through and actually calculated the length of the radius and then plugged it into the surface area formula, or you just want to look at this and go, well, it would be a lot faster just to take the 38, put it into the area part of the surface area, or the area, the circle area, kind of think of it there, plug it in there, and then you just have 4 times 38. This method's going to be faster, but sometimes we forget those things. Take your pick. And then my last one would be, I want to find the surface area of a hemisphere. Now remember, a hemisphere is a sphere that's been essentially cut in half, and we know that the radius of it is 3 feet. What I'm going to do first is I'm going to draw kind of my picture of a hemisphere. It looks something like this. And what I want you to think about is when you take a sphere and you cut it in half, yeah, you're going to eliminate half of the surface area. So now we only have this part of what used to be the full sphere. But when you cut it, you opened up the inside and you now have that circle showing. That's something you can touch. That's part of the surface now. So we have to find the area of, kind of think of the curved part of the hemisphere, and then we have to find the area of the flat part, which is the circle. So the first I'm going to do is I'm going to find the surface area of the green part. So that, I'm just going to use my old formula of 4 pi r squared, but then I'm going to have to cut it in half because we only have half the sphere. Now when I plug my numbers into this, I'd have 4 times pi times 3 is my radius squared, and all divided by 2. Now if I go with the exact value here, 2 is going to become 1, the 4 is going to become, 2, and then 2 times 3 squared, or 2 times 9 is 18, I'd end up with 18 pi for the area of the green portion. Now the red circle, that's the area of a circle, that's going to be just pi times 3 squared. That's going to come out to be 9 pi. So now I just need to take the area of the green part, 18 pi. I need to add it to the area of the circle, which was 9 pi. And I'm going to have the area of my hemisphere, which is going to come out to be 27 pi. My label for this problem was feet, so 27 pi feet squared. The approximate area would be 82.882. Oops, nope, I rounded that wrong. I did that wrong. Not 82. Try again. Let's go with 84.82 square feet. Something I want you to remember about this is some hemispheres will have what I refer to as the solid top, and you actually need to calculate the area of the circle, but some of them will be more like a bowl where there's no cover on it, and then the surface area is going to be different. So you have to look at what kind of hemisphere it is. If it talks about it like it does in this problem, assume that it has a top that you can calculate the area. Sometimes it might be a bowl, and it may ask you just to calculate the surface area of the outside portion of it. So keep that in mind when you're working with surface areas of hemispheres. And that's going to conclude the example portion on surface areas of spheres.